Guys, this presentation will be held in English, just to let you know up front. And what I will be talking about is distributed systems fault injection testing using Docker. This will be the story of the project I've been working on since I joined the base a couple months ago. Okay, so quick intro. Let's talk a bit about failures in microservices architectures. Then I will describe our particular case study of the use of Elasticsearch database in base, and the solution for the problems that we introduced to solve. I will talk briefly about testing microservices. And describe the fault injection test toolkit that we've assembled for this very purpose, and give you some examples of how it works. So microservices, pretty hot topic, actually hot enough for most of you to attend at least a couple of lectures so far regarding them, so I won't duplicate any of this knowledge. But some key features, they are hard to do, even harder to do right. But we still do this because we get some very interesting benefits from that. It's scalability, it's resiliency, it's fault tolerance. This is what we want, but we have to pay for this. There are some pains associated with first thing that we should remember about is CAP theorem. This is somewhat simplified approach, but it works in various situations. So to recap briefly, this says that from the free consistency, availability, and partition tolerance, we cannot get 3 at a time, we can only get two. But since we are talking about distributed systems running on network, network will fail. And we need to be prepared for that, so we need to reserve the partition tolerance up front. So actually the choice is between CP, consistent and partition tolerant systems, and AP, available and partition tolerant systems. This is the choice that we have. And we will see how this works in our particular example of application that we were developing. Our application belongs to cloud. We don't want to create our own data centers to get busy with servers, with the environment. So we just want to deploy them to the cloud provider, possibly take advantage of auto-scaling features, and it should work up front. So as I said, network will fail. There's this thing called fallacies of distributed programming. The first and most important is this network is reliable. Network is not reliable, network will fail. It will fail us drastically in the time that we want it not to. And just an example that those are not empty words, in base, which is hosting its microservices on Amazon. This year we had 2 hours of network problems, which was uniquely assigned to Amazon problems. So the only thing we could do was to get prepared for them. We couldn't make sure they won't happen because they will. So as I said, 2 hours this year. And also the hardware will fail too. So considering the standard SSD drive that should last about 10 years on moderately heavy load, if we're talking about the average Amazon data center that consists of about 80,000 physical machines, we're getting 20 physical crashes of machines every day. So such a hard drive needs to be located, needs to be replaced. This takes time, and our application will most probably be down for some time due to this. Of course, the routing algorithm and auto-balancing will replace our instance, but at some point we will find out that the machine crashed, and we need to recover from this. Once again, example from base, which is running hundreds of Amazon machines on production. Every week we get at least 1, more likely up to 5 crashes related to physical machine crashes in Amazon. So the problem is real. We need to handle this. And also, since the scale of the whole endeavor, we need to be prepared for the things are not that obvious to predict, actually. Like, for example, when the Facebook data center was drenched by actual cloud, when they had misfunctioning cooling systems and the air cooled down under the roof, and the actual rain cloud formed in their data center, and the cloud was drenched by the cloud. So pretty ironical example, but once again, this is what we need to be prepared for designing our applications. And case study. In Base, we are using Elasticsearch database. This is distributed database. We store some client's data in it. And since it's distributed in nature, it stores data in multiple shards. So we need some way to determine which shard the data should be stored in or fetched from. And we so far do this by client's account ID. So we get a request from client, give me that piece of data, we check what's their ID, and we go to appropriate shard based on this ID and give the client a data. And it worked pretty well for a long period of time, since from the very beginning of functioning Base, we had multiple small to average sized clients. They were evenly distributed. It worked fine. But at some point of our growth, we experienced getting larger and larger clients. So it's not only we're getting larger clients, but the accounts. What's happening? Okay. But the accounts in terms of users per account also grew. So this is the situation that we found ourselves just a couple months ago. We get this one big client that eats up all the resources on one physical machine, all the CPU, memory. So it started to slow down for this client and for any other client that might end up on the same machine. And apparently, this approach didn't scale well starting at some point, but it worked quite nice for most of the others of clients. So on one hand, we wanted to maintain this approach for most of the clients, but we would like to be able to handle some of them differently. And we wanted to get prepared for the problems yet to come that we might not know about now. So, for example, we would like to provide SLA, service level agreement, for our clients to the access to the data. And one of our most important concerns, we wanted to prioritize interactive traffic, because it's not that important whether the static data import lasts 11 or 15 minutes. For example, some external integration, but it's quite important whether the user, after clicking in browser or in the mobile app, gets the response within tens of milliseconds. So this is what we wanted to handle at this opportunity. And also it would be nice to configure whole thing dynamically as the situation changes. For example, if one client grows and becomes problematic, we could start treating them differently on separate cluster of Elasticsearch. And as wise folk said, all problems in computer science can be solved by another level of indirection. We took this approach since it was confirmed it works quite nice. And we introduced an application called Elastic Proxy. So the idea is simple. Since now our client services won't be connecting the Elasticsearch database directly, instead they will be contacting a proxy. And the proxy will take care of dynamic configuration, traffic routing, additional monitorings, things like that. We have multiple services consuming database services, and we wanted this change to be as transparent as possible. We didn't want any code changes or even extended configuration changes. We just wanted to switch the URL from the database to our proxy, and it should work fine. So the architecture says that there's one central component that should be as lightweight as possible. This is the proxy itself. But we also would like to be able to configure whole thing dynamically. This is what the proxy sidecar is for. This is the application that handles user interaction. User in this case is a developer and someone who wants to change the configuration. And it configures with the proxy through the Zookeeper cluster. So that configuration responsibility is delegated to the sidecar, and the proxy is responsible solely for the traffic routing, which so far works nice because we get delays of 3 to 4 milliseconds, which is acceptable for the quite complex logic and virtual database topology we're introducing underneath. So after we have developed it, we wanted to test that, and up to some point, the testing microservices architecture is no different than any other. We need to extend a suite of unit tests that covers basic functionality. They are very fast to execute, so we get fast feedback loop. We don't have to wait minutes or hours to check whether our system still works correctly. We get that within seconds or maybe a couple of minutes in terms of more complex builds. But then we also need some additional level of security to, for example, check our communication layer, database access, things like that, integration test. So as long as we're talking about testing single service, our routine would be exactly the same as for the monolith application, but then we're getting on the top of the testing pyramid as defined by MacCon, and this is the point when things start to get complex. Because since we are now testing system, we would like to have multiple services tested, deployed, possibly with multiple versions, all those hard things that are usually mentioned when we're talking about microservices. So these new challenges require new approaches. And what are those challenges? First of all, we're getting to the non-deterministic world. And it's non-deterministic because it's extremely complex, and we cannot test it effectively with all the possible variants. For example, this chart is production traffic profile from base, taken a couple days ago. So services, points at the circle are services, and the lines between them is traffic. The wider the line, the higher the traffic is between two services. So this is basically a mess. There's more than 100 services here, and to mimic this all in testing environment would be nearly impossible. And even if it was possible, by the time we tested the whole thing, our business would be probably down a long time. So we need to make simplifying assumptions, we need to make trade-offs, and we need to know when and where and why we need to make them. So I will go back to it, and there's also fault space complexity. Our fault space itself is quite complex. Even in a relatively simple application like this, we have two services, one configuration database, one data database, a couple client services, that's all. But many things can fail in here, various network connections in different configurations. For example, some application can be partitioned. So this is all what we need to be prepared for. And to give you a glimpse, even the network problems themselves are a pretty complex topic that would take much longer than this one talk to cover. Because, for example, there are 4 basic models to simulate the network problems in terms of package loss. So there are different probabilistic models. Even if you were only to consider a network, we're getting in very complex details pretty far. So we need to stop at some level and be able to say that, okay, this is how deep we would like to test this. Yeah, this is basically what I said. And an interesting approach of that is Netflix's Chaos Monkey framework. This is quite a cool thing because they're running it on production. And it's messing with their production services every day because they claim the failures will happen anyway. So you would most probably like to get notified about them having drunk your morning coffee, sitting at your desk, then late at night being on call. So they are running in on production, and this is quite an interesting approach about how they monitor this solution and problem space. They use an algorithm called lineage-driven fault injection, and what it basically means is that instead of exploring all the possible failure solution, they execute one successful request, and then they ask, why is this request successful? So once they get the answer why the request is successful, they can ask questions like, what can we do for this request to fail? And using this approach, they were able to find 5 critical failure points in their app boot, which is the process that starts client's application. They want to be able to provide the best experience since the very start for the customer to be satisfied. So this is described on the blog, but bottom down is that instead of 2 to 100 iterations that would be required in brute force approach, they managed to do that in 200 just simple production experiments. So this is quite a gain, and this is what they were aiming for. But it won't be suitable in our case, because first of all, we wanted a deterministic set of tests, not a random one. And we wanted to place that earlier in development lifecycle, not on production. So we introduced a framework based on the couple of publicly available tools. And I will describe that briefly. So first of all, we used Docker, Docker Compose to be specific. Docker Compose is quite a cool tool. It allows to define your environment using configuration file, store that somewhere on your disk, and then spawn whole environment using one command. So you don't need to deploy to multiple servers. You don't need to deploy it even to cloud. You can set up whole thing locally. The application consisting of a couple of Elasticsearch instances, Zookeeper cluster, Spring Boot applications, Grafana for metrics, some additional tools can be easily hosted on a PC class computer, and it works pretty well. So just to give you a glimpse of that, this is the example configuration file. And it's quite simple, actually. On the top, we can see an Elastic One instance. We want to have a couple instances. We just specify source image. Images are publicly available over the internet. So if you just type Elasticsearch, the Docker Compose will download the image for you, spawn, bang, you have database running locally on your environment, and you can start playing with it. Quite nice. You can customize commands. So for example, we use it to form multiple clusters of the Elasticsearch, so we can verify our routing works correctly. If there's partition, the whole system behaves like it should do, things like that. Also, 2 more things visible here. You can expose ports of the container to your system, which is nice, for example, if you would like to execute requests to your application via curl. Then you can just expose the port. You have access to your application running on a container. One other thing, you can do some additional things with the file system mounting. So, but the bottom line is just couple of configuration line. You have your environment up and running, which is nice because it allows you to be productive and to focus on real work instead of plumbing. So we get all these common dependencies publicly available over the internet. Now we would like to introduce services that we develop and we would like to test in this. We use Amazon Web Services for it, which is part of the publicly available Amazon Cloud Services. We just use Docker to push image to our repository, which any base team member has access to. So if you would like to test your application communicating with microservices developed by other teams, no problem. You just point your application to the ECR, which stands for Elastic Cloud 2 Container Repository. And here it is. The only change here, you can see it's on the top. The image now consists of the ECR repository name in front of it. And you have it all up and running. You have access to all the dependencies, internal or external. It works quite nice. So once we have our environment set up, we need to start our testing routine based on some kind of framework. We used BATS for it. BATS stands for Bash Automating Testing Suite. And as the name suggests, it's Bash-based, so it might be a pain in the neck because, let's be honest, Bash is not the most elastic tool to work with. But in this particular case, it did its job pretty well. It gives you a really simple set of functionalities, like execute some bash commands and make very simple assertions on it. So here is how it works. This is the bash-like script. You can use bash commands. So for example, you can abstract away your common dependencies or code if you have procedures that are used in multiple tests. And you just include them as any other bash scripts. And the test format is test annotated method with some meaningful name. And here inside it are just the regular bash commands. So in here, we just assume we have our environment set up. We execute curl towards one of our service through exposed port. And then we verify through Bat's assertion system that the result from the command is as expected. So really simple, nothing complex, but it gives you quite powerful opportunities to build upon this simple concept. And now, as proxy fault injection tests, we needed something to actually inject the fault as we're speaking. So we found a tool called Pumbaa. This came up during our work in a develop team, so we just found it. Even though it's relatively fresh, we decided to use it because this suited our needs, so there was no need to talk about it too much. So, as I said, currently version 0.2.6, still fresh, but works quite nice. Pumbaa is a Docker tool that manipulates containers, and it allows you to inject all kinds of failure into your Dockerized environment. It has multiple options like stopping containers, restarting them, manipulating networks. And in terms of network, it uses Netem. Netem is a Linux utility tool which works on the kernel level. So it does some magic to packets. It can delay them, it can reorder them, anything to simulate faulty conditions in microservices environment. You can do it here. Okay, so we extend our testing suite with Pumbaa. And spinning Pumbaa up is just a matter of running appropriate Docker container with it. So most of this line is actually configuring Docker. You specify image name, which is Jaya adm Pumbaa. It downloads it automatically from the internet. Then you specify command you would like to execute in your test environment. In this case, this is package loss of 8%, affecting containers specified in the last parameter with the duration of 10 minutes. So this way you can verify how your application will behave if the network is faulty, if there is 8% package loss, which is actually quite a lot. But it's perfectly reasonable to test under heavy faulty conditions. So once we have all the tools set up, what do? We need to identify the most obvious failing points. And in our architecture, this would be probably communication loss between database and the proxy, or between the sidecar and Zookeeper, things like that. So this is a pretty simple starting point when you can test how your application will behave and whether this is what you expect. So once again, a relatively simple command that would most probably be stored somewhere in your utility script. So you would like just to type enable package loss or something like this. You specify 100% target containers, and you have it. Now you have broken network connections between your services. You can start making assertions. So this works quite well. We use that. Another kind of problems. As I said, since we're working on the distributed systems, we need to mind the cap theorem. Like, for example, Zookeeper itself, as we consider it a single dependency, is distributed system itself. It's a cluster of nodes, and it also obeys cap theorem. And as for the Zookeeper itself, it's consistent system. which means that if there's if it loses a quorum, which means it will be splitted into two parts, in one of which will have less than half of the initial number of nodes, it will stop accepting any data, because it's say, okay, we cannot decide whether it's legal to accept those data. We'll just wait for the quorum to be restored, and it will hang indefinitely. But Elastic Cluster, on the other hand, is available system, so it chooses to operate even by the cost of the storing inconsistent data. And this even has a name. It's called the brain split, and it's the situation when Elastic Cluster is divided into two parts, and they keep accepting the data, and at some point the data might diverge. It is impossible to merge them into a consistent state again. So you would probably like to configure your Elasticsearch cluster to not to behave like this, but to stop accepting requests and be more like Zookeeper in this case. But once again, this is something you can easily test using described framework. You can just define which node should lose connectivity with which, and then you can start making assertions whether the cluster behaves correctly and the whole system works nice. And also all other kinds of problems. So now we're not dealing with binary connection losses, but we're getting network that is congested. There may be delays, package drops, reorderings, and we would also like to be sure that our application behaves correctly in such conditions. So here's an example of the single test scenario. This is quite unfortunate, but the unit on the y-axis are nanoseconds. So 1 billion would be 1 second in this case. But at some point, the application was operating normally. The response times were within a couple hundred milliseconds. It was OK. Then we enabled 800 milliseconds global delay. And this is actually what we should expect. The response time from the Zookeeper database increased up to about 800 milliseconds. Easy peasy. But then we enabled global package loss, and we disabled the delay, and we get even higher response time. So by the profile of the communication that Zookeeper performs with our application or with the cluster node, we can see that package loss is much more dangerous for the application responsivity than the delays, because it has to do retries, it loses some data. So this is actually quite relevant source of information in terms of reverse engineering if we are expecting some issues on production, and we have charts like this, we can reason about where they come from. So this was one of the findings, and not very surprising. In terms of the whole application, those delays accumulate, and they are multiplied because when the application accepts configuration, it validates it, it checks whether the clusters specified in the topology are actually Elasticsearch clusters, whether they are available, whether their status is green, things like that. So this accumulates, and even under the network delaying by 800 millis, we get application response time up to 15 milliseconds. So this is yet another important information. Maybe there's space to improve, to execute more things in parallel, things like that. So this is the insight you would be looking for executing those kind of tests. Okay, so I will sum up quickly. Failures will happen. As we know, they are happening. Those are not empty words. On production, they are happening every couple of days. So we need to be prepared for them. And we would like to design our application to handle and embrace that fault up front. This pays off. We get some better levels of security, and we are more confident that our whole system and whole environment will work nice. But this is still not enough. We need to do some tests, and life shows that the best tests are done on production. So we would like to do most of it as early as possible, in this case by setting up some environment to mimic the cloud conditions as closely as possible. And once again, this is not a silver bullet. Those tests are only as good as you want them to be. You can spend more and more resources on it. You can create more and more complex test scenarios. And by doubling effort, you will get less and less gain. So there's a point when you need to stop, when you would like to say, okay, this is what we were looking for. This is what we wanted to test. And we're sure it's okay to go for production. That's all from me. I'm open to questions from you. Okay, so I guess there are none, but if you can think of anything regarding this presentation or any other system that we are developing on base or the work in the company, you can contact me. You can check out our Java blog. This is my email. Those are 2 Twitter accounts. Thank you for your attention.